Alright, so why is this a rational function? Why is it not a linear function? Why is it not a quadratic? Okay, thank you. Yep. Why is it a rational function? Julia said because it's a fraction. It's a ratio, right? It's a rational function because it's a fraction. What's a linear function? What's the most common linear function you think of?
Y equals mx plus
Y equals mx plus b. Yeah, does this look like y equals mx plus b? No. Okay, maybe on the top, but that's not the only part of the function. So that's not a quadratic function. What's a quadratic function?
x squared.
Ax squared plus bx plus c, something like that. Okay. So it's not any of those. This is a rational function because it's a fraction. It's a ratio. All right. So the things that you will not want to know for rational functions, some of them we've done before. Probably the most common one I'm going to ask you is, okay, does this rational function have a vertical asymptote? Okay, so the first thing I'm going to ask you is, does it have a vertical asymptote? How do you know? What are you going to have to do to determine whether it has a vertical asymptote? Assuming, we're going to try and do this for the most part without a calculator. All right? Thoughts?
Try to factor the bottom.
Try to factor the bottom, because what are you interested in figuring out? When the bottom equals 0, yeah. Okay. And I don't want to sit here and guess and check plugging in numbers for x to see what makes the bottom equal 0, so I'm going to try and factor the bottom. Okay. What would the two factors be on the bottom? X plus 5 and x plus 7. Nice. Okay? So x plus 5 and x plus 7 would be the two factors of our denominator. Now that we factored the denominator, can you tell where the vertical asymptotes, or at vertical asymptote, would be? Where at? At -7, but not at -5. Okay? There will be a vertical asymptote at x equals -7 because that is an x value that makes only the denominator equals 0. Okay? So the vertical asymptote will be at x equals -7. And if I ask you why, you would say, because that is an x value that makes only the denominator equal 0. So not only do you want to know where the vertical asymptote occurs, you might want to be able to explain how you know the vertical asymptote occurs there. And it's because that is the x value that makes only the denominator equal 0. One more time for those of you that just need to memorize it because you don't write it down. The vertical asymptote occurs at the x value that makes only the denominator equal 0. Okay? So there's our vertical asymptote. We'll go to holes next. Okay, we've done this before. Will this rational function have a hole?
Yes.
Yes. At what x value?
-5.
-5. How do you know?
Because it makes the bottom and the top equal 0.
Because it makes the bottom and the top equal 0. So you know there's going to be a hole at -5 comma some y value, right?
Yeah.
But it definitely has to have an x value of -5 because that is a value that makes both the numerator and the denominator equal 0. How do I figure out the exact location of the hole if I know the x value is -5? Plug x in, or plug -5 in for x. Can I do it into this function right here? No, if you do, what do you get? If you get 0 over 0, which is undefined. That's not an answer. Okay? So what do you have to do?
Plug it into the original.
Yeah, cancel out your common factors, and now you just have 1 over x plus 7, right? Now can you plug in a -5 for x and get an answer for y? Yes, -5 plus 7 is 2. 1 divided by 2 is 1/2. So this particular rational function has a vertical asymptote at x equals -7 It's got a hole at -5 comma 1/2. Okay. Let's do the domain of this thing. What's domain again? X values. Values you can substitute in for X and you'll expect to get an answer for Y. Okay? Well, what values can I plug in for X and get an answer for Y? All of them except -5 and -7, right? If I try plugging in -5, I'm going to get undefined. If I try plugging in -7, I'm going to get undefined. But I can plug in any other number for X. So my domain will be every number from -infinity to -7. And then every number from -7 to -5. And then every number from -5 to positive infinity. Okay, so there is your domain. The next thing I'm going to do is I'm going to do horizontal asymptotes. And that is something a little bit new. Horizontal asymptotes occur at the very, very far left and the very, very far right of the graph. Okay? In fact, I'm going to go off on a little side note here, and I'm going to talk a little bit about horizontal asymptotes, because you probably don't have much for notes on those. Horizontal asymptotes occur at the far left and right parts of the graph. That's the very general way to put it. Okay. A little bit more mathematical way to put it is they occur when X approaches positive or negative infinity. So as X values get really, really big, or as X values get really, really small, okay, as the X value goes towards infinity, which is like saying as you go to the right, or as the X values approach negative infinity, which is like saying to the left, okay? That's where horizontal asymptotes occur. They really don't exist in both directions forever, okay? So if we say something has a horizontal asymptote of y equals 1, sometimes a graph might cross y equals 1, kind of near the origin. But I guarantee you, as x goes to positive infinity, the graph will be getting really close to that horizontal asymptote. Okay? So it's a little bit different. Vertical asymptotes a graph will never cross. Horizontal asymptotes are imaginary lines that the graphs get really close to, but they only get really close to those values way to the right or way to the left. They could potentially cross that imaginary line somewhere in the middle. Okay? So, that's another thing on horizontal asymptotes. Let's see. Without showing you what I mean, I don't know if I need to add any more here. Okay? So, I'm going to talk you through it logically, and then I'll show you on a calculator. So a horizontal asymptote is going to be what a graph is approaching as x gets really, really big. Okay? So if you look at this, let's say we were plugging in very large x values. Okay? 100, 1,000, 1,000,000, 1,000,000,000, and so on. Okay? What would you think this ratio, or this rational function, will get really close to as you plug in bigger and bigger and bigger numbers for x? Any ideas? Any guesses? What's going to be happening to the y values as I plug in 10,
We get
20,
smaller.
30, 40, 100, a billion, so on? Colin, what do you think?
Smaller,
Smaller and smaller? Why? You're right.
because when you divide by, because when you plug in a number for x on top, you also have to plug in for the bottom, so the numbers just keep getting bigger and bigger, and they can never go below
Well-
0.
Won't the bottom numbers get a lot bigger, a lot faster? How can you tell? It's got an x squared in it, okay? I mean, let's just take the number 10 for instance. You know, I'll ignore the rest of this, you know, because 10 divided by 10 squared is 10 divided by 100, or 1/10, right? Okay, yeah, that's a small number. Let's try a million. A million divided by a million squared. That's 1/1,000,000th. That's a pretty tiny number, right? You can add the 12 million if you want to it, but 12 million is like pocket change compared to a million squared. Okay? This really has no impact on this. The bottom is going to increase much, much faster. Everybody agrees?
Yeah.
So this ratio is going to approach 0. This graph is going to approach 0 as x gets really, really big. So there's going to be a horizontal asymptote at y equals 0. Okay? I'll show you on a graph here. Maybe. Alright, so what I have on the top, x plus 5.
Yes.
So if I'm going to graph this, I'm going to put x plus 5 on the top, divided by, and then in parentheses I got to put the rest of it, so that was x squared plus 12x plus 35.
Yes.
See how I'm entering this into my graphing calculator? Any questions? So here you can kind of tell, here's the graph. We knew we'd have a vertical asymptote over there at -7, I think it was. Okay? And otherwise the graph just looks like this. It's approaching 0. It's getting really, really close to 0 this way. It's actually getting really, really close to 0 that way too. So there ends up being a horizontal asymptote at y equals 0. If you can't quite tell, here's another method I'll use. I'll go to my table setup, and I'll say, alright, table of values, I want you to start at 0, but I want you to count by 100. So look at what's happening to the y values as x is getting bigger. What's happening to the y values? Getting smaller, getting closer to 0. Okay? How about as x goes to negative infinity, or as x goes to the left? Notice what's happening again to the y values. Getting closer to 0 again, right? Okay? So I can tell both from the picture of the graph and my table of values that this function will have a horizontal asymptote at y equals 0, because the graph was approaching 0 as I go away to the right, and the graph was approaching 0 as I go away to the left. Okay? So that tells me then there's going to be a horizontal asymptote at y equals 0. Okay? So I showed you how to do that using a table of values on your calculator. I showed you how to do that using the picture of the graph from your calculator, and I kind of talked you through it logically. Okay? The bottom's getting bigger faster. What happens when bigger numbers are on the bottom of the fraction? The fractions get smaller, closer to 0, right? Okay? So my horizontal asymptote here was y equals 0. Okay? Then the last two things I want to get here are x and y intercepts. Okay? X-intercept. What is an x-intercept? What is an x-intercept? Nice, where the graph crosses the x-axis. Okay? The x-intercept is where the graph crosses the x-axis. What is the y value at any x-intercept? 0. So how are we going to find the x-intercept of this function. Plug in 0 for y, and solve for x. So 0 equals x plus 5 over x squared plus 12x plus 35. Well, this is easy. The only way this fraction equals 0 is if what? How can a fraction ever equal 0? If the top equals 0, right? I mean, there's no other way for a fraction to ever equal 0. So, what value of x would result in the top equaling 0?
-5.
-5. Okay? So, initially I'm going to get x equals -5 for my x-intercept here. Okay? Because that is the only x value that would make this fraction have a 0 on top. However, you got to think back a moment. Will this be where the x-intercept is located? No, because what did we have at -5? We had a hole. Okay? We had a hole. This graph doesn't even exist at x equals -5. There's a hole there. So this graph never touches the x-axis. So therefore there are none. Okay? That's impossible. Algebraically, we got this for an answer, but we know it's impossible because what does -5, not only, I guess -5 does make the top equal 0, but what else?
Makes bottom.
It made the bottom equal 0, so therefore this is not where the x-intercept is located. There is no x value that will ever make y equal 0. So there are no x-intercepts. Y-intercepts are usually much easier. A y-intercept is where a graph crosses the y-axis. What is the x value? 0. So all you do is you plug in a 0 for x. So y equals 0 plus 5 over 0 squared plus 12 times 0 plus 35. See what I did there? Just plugged in 0 for x. Answer 5 over 35 or 1/7, right? Did I do my math right there?
Yeah.
Okay. So my y-intercept is 0, comma, 1/7. Okay? So, we did vertical asymptotes, poles, domains, horizontal asymptotes, x-intercept, y-intercept. Any questions on that? Okay? One last thing here, I'm going to go pretty fast through it. You're going to have a problem that asks you to write the function. And I'm going to give you the information. So I'm going to say the vertical asymptotes are at x equals 3 and x equals -1. I'm going to say there's a pole at x equals 4. And I'm going to say that, I'm going to say that if I plug a 0 into the function, out comes a 3. I'm going to give you that information and say you write the function represented by that information. If there's a vertical asymptote at x equals 3, what do I need in the denominator? X minus 3. If a vertical asymptote occurs at x equals -1, what do I need in my denominator? X plus 1. Because I know these values are what make the denominator equal 0, right? If there's a hole at x equals 4, what do I need up here on the bottom? X minus 4. Okay? And I also know that if I plug in 0 for x, out comes a 3 for y. That's probably the trickiest part. Okay? I know that if I plug in a 0 for x, out comes a 3 for y, so here's what I would do. More likely what's going to happen is there's going to have to be some number up here, so that when I plug in a 0 for x, out comes a 3 for y. So here's what I would do. I would say 3 equals a times 0 minus 4 times 0 minus 3 times 0 plus 1 times 0 minus 4. Because I know that if I plug in a 0 for x, I need to get a 3 for y. So I plug in 0 for x, I plug in 3 for y, and then I just figure out what that a value needs to be in order for this to be true. Alright? So 3 equals negative 3 times 1 would be negative 3 times negative 4, that would be 12. There's a negative 4 on top, so I have a times negative 4 twelfths equals 3. Solve for a. So I multiply by
12 over negative 4.
12 over negative 4, that'd be 36 over negative 4, negative 9. So a equals negative 9. So now I'd write my final answer, f of x equals all of this, but I'd throw a negative 9 right out in front. And that would be my answer. Here is a rational function that would satisfy all that information.
Are you wanting us to FOIL it out and stuff
Nope.
on the bottom?